Hi, and welcome to this clip going through the paper from 2010. We're going to focus on question 3 because this particular question is quite accessible to first year students because it covers first year topics. So you've got oxidation numbers and redox, which is generally done in your first term. We've got constructing and balancing chemical equations, which moves on from GCSE. And we've got enthalpy calculations and Hess's law. So if you haven't come across enthalpy calculations just yet, if let's say you're in your first year, these are generally taught in the spring term, which is after when you take the chemistry Olympiad. So they sometimes teach it in maybe end of February, beginning of March, and the chemistry Olympiad paper is usually taken in the end of January. So to try and make sure you're not at a disadvantage, I'll slow down a little bit when we come to the enthalpy part and do a little bit of background as well, but try and keep the pace going too. Okay, now it's worth having a look at some of the bullet points that they print on the first page, the top sheet of the paper. So it's very important to make sure you always use good mathematical practice when you're doing calculations in chemistry Olympiad papers. Things like the correct units, in other words, the correct conversions if necessary, appropriate significant figures, in other words, the least sensitive number of significant figures from the question itself. And when we say clear calculation layouts, that means making sure that you lay out the appropriate steps, at least the main steps, so that the examiner can see the logic behind your calculation. So at the bottom, it talks about some of the questions will contain material you have not been familiar with. So what they want to do is on purpose do this, so it puts you off your stride and it makes you use your problem-solving skills instead of relying on recall of facts. So this is something that's key to all chemistry Olympiad papers. That's why it's more challenging. So a quick word on the periodic table that comes with the paper. You need to use the relative atomic mass values from the periodic table that they provide because they're quoted to a higher degree of precision. In other words, more decimal places than you're normally finding in a textbook or an exam board version. These are closer to what you'd use at university. So the thing to do is to use these values as opposed to values you might have remembered from GCSE or from your A-level work. So at the start of every chemistry Olympiad question, you'll get some contextual information that gives you a feel for the substance or the chemistry that you're about to be tested on. So part A asks you to construct a balanced chemical equation from information about a reaction. So let's think about the information that we've got. The first sentence says ClF3 is used to turn uranium into uranium hexafluoride, which is used to separate the isotopes of uranium. Chlorine monofluoride is a side product in the reaction. So now we can decide what to put down as our equation. So the first thing you do is to write out what you know already on the reactant side and the product side, and leave spaces for balancing numbers. So we don't know what the balancing numbers are yet, so if you leave spaces to put them in, that'll be quite useful. So we know that there are 7 fluorines on the right-hand side, but only 3 fluorine atoms on the left-hand side. So we also know that uranium is already balanced, so if we can avoid it, try not to multiply up UF6. So if we leave UF6 alone, what can we do with the other fluorines? So what we do is multiply by 3 on the left-hand side to give us 9 fluorines, 6 of which are used up in UF6, so the remaining 3 that we need can come from multiplying ClF by 3. So the next question, part B, asks us to consider the equation and think about what might be being oxidized. So it asks you to circle each atom or ion on the left-hand side of the equation that is oxidized in the reaction between chlorine trifluoride and silver chloride. But the most important thing to remember is it said that ClF3 is an oxidizing agent. So they tell you this already, so therefore the other reactant should be the oxidized, it should be the thing that's being oxidized, so you should be circling AgCl. But ideally, because the instructions say each atom, we should be circling Ag and Cl separately. So in part C, they introduce a new word called disproportionation. So this means the simultaneous oxidation and reduction of the same element in a reaction. So for this to actually work, you do need two, at least, atoms of the same element. So one is oxidized and the other is reduced. You can't oxidize and reduce the same atom at the same time. So it's worth just taking a moment to look at the information they give you before we start trying to work out the equations that they're asking you in part I. It says when the oxidation number of iodine is between 0 and +7, there's a possibility that it will disproportionate to the compound with iodine in its next highest oxidation number. So the oxidation number will drop down by 1, or the next lowest one that's there, and also produce elemental iodine. So for example, if it was oxidation number +7 and then there was another compound that had oxidation +6 for iodine, then iodine would drop to oxidation number +6. So it asks you to give the equations for the theoretical disproportionation reactions of IF, IF3 and IF5. So in each case, what I've done is left spaces for the balancing numbers and how many fluorine atoms there are in the iodine fluoride product. So if we start with the first one, looking at the product we're going to make, the iodine fluoride product, we have to choose from any of these four. So what I've done is I've put down the oxidation number for iodine next to each one. So then it says the next highest oxidation number. So that means that it's going to make IF3. So we've got 3IF giving you IF3 plus I2. Now in IF3, the next one, the next oxidation number up for iodine is +5 in IF5, which gives us 5IF3 going to 3IF5 plus I2. So the next one shouldn't be too difficult. Obviously, I put it in there, going from +5 to +7 gives you 7IF5, giving you 5IF7 plus I2. So I mentioned a little earlier on in the clip that when we come across the mention of standard enthalpy change, I'll slow down a little bit and explain what it's about, just in case you're doing this clip and you haven't come across this idea yet. So you will come across it in your A-level, in your first year, and it's basically a standard enthalpy change is the energy transfer, usually in the form of heat, when 1 mole of a substance undergoes some kind of change. So it relates to exothermic and endothermic reactions from GCSE. So Hess's law governs standard enthalpy changes. So an enthalpy change for a reaction remains the same and is independent of the route taken. So standard conditions refer to 298 Kelvin and 100 kilopascals of pressure. So you'll notice that the data you're given is actually standard enthalpy of formation because it's delta FH. So H stands for heat energy, delta little triangle stands for change in, and the little f stands for formation. So in case you haven't come across it before, the definition of formation in this sense means the enthalpy change when 1 mole of a compound is made from its constituent elements, all reactants and products in their standard states. In other words, those values, minus 95.4, minus 486, and so on and so forth, is the amount of energy in kilojoules when 1 mole of that compound is made from elemental iodine and elemental fluorine. It's worth pointing out that elements have 0 for this particular value because they're all formed at the start of the universe and have simply undergone lots of chemical reactions since that time. So this is what a Hess cycle for combustion data would look like. You'd have your combustion products, usually oxides, at the bottom, the reactants going to your products at the top, and the grey arrow represents an enthalpy change. And there'll be one missing that you're trying to calculate. That's the one that goes across the top. The ones that point down are the ones you already have. So the indirect route is using enthalpy values we already know. So you work your way around the dotted line, adding up the enthalpy values from the table, but reversing the sign if the direction of travel is opposite to the enthalpy arrow. So for example, on the right-hand side, you'd reverse the sign because the blue arrow, the dotted line, points in the opposite direction to the grey arrow. On the left-hand side, you'd keep the sign the same. So let's imagine that you had formation data, which we do in this case. The layout is slightly different. You'll notice that the arrows point from elements to reactants and products this time round because of the definition of standard enthalpy of formation that we talked about a bit earlier. And the mathematics is handled exactly the same way. So now we can start putting in the actual reactants, products and elements according to what the question wants. So taking the first reaction, we write in delta RH to represent the enthalpy change we're trying to work out, and you'll notice that the elements as listed in the box can form either the reactants or the products. So what you have to do is insert the numbers and follow the dotted line. So you'll notice minus 95.4 is changed to plus 95.4 because the dotted line is going against the direction of the enthalpy arrow, the grey arrow. There's 3 IFs, so you multiply it by 3. So that gives us minus 199.8 kilojoules per mole to the minus 1. So in a similar way, we can do the same calculation for the second reaction. And not surprisingly, we can do the same for the third one. So for this third one, we get plus 1088.5 kilojoules per mole. So the final part asks you to suggest which one out of the 3 iodine fluoride compounds doesn't actually disproportionate. It told you at the beginning, give the equations for the theoretical disproportionation. Theoretical means it may happen, but it also may not. Now the fact they've asked you to do this after you've worked out the enthalpy values has some significance. So if you look at the enthalpy values, 2 of them are exothermic, meaning that they release energy, but 1 of them is endothermic. If something's endothermic, it means it's got to take energy in before it happens. So therefore it's less likely to take place unless there's energy input into the system. So therefore the correct answer is IF5 because it's endothermic delta RH value for its disproportionation. Okay, then that takes us to the end of this clip. Hopefully it's been a useful introduction to some of the areas of A-level chemistry that might come up in chemistry Olympiad papers. If you're a second year, hopefully it's been a useful review of Hess's law from last year. But either way, all the best in taking the paper, and hopefully it also gives you an idea of how to use sort of problem-solving, deduction-style thinking rather than recall on its own. So in the meantime, until I see you again, thanks for listening and see you soon.